Hi everybody, welcome back to Chem 140. I'll turn the music down here. There we go. What do we got going on this week? So we're going to do units 13 and 14. 13 is pretty short, 14 is not very long either. And then we have the last 2 weeks to do units 15 and 16, and then we're done. So we're actually really close to the end, which is exciting because I'm sure you're all sick of this, right? I forgot that the quiz was for Unit 12 only. I thought it was 12 and 13 for some reason. So a quiz is going to go up tonight for Unit 12. It'll be due next week. My forgetfulness means that there's no quiz due this week. Just the lab worksheet, which is due on Wednesday. So there's a quiz on 12 and 13. 12. There's a quiz on 13 and 14. And then the last quiz is 15, 16. I think. There's 9 quizzes, and we've done 6, right? Yeah, so. Alright, cool. That's where we're at. So, yeah, without further ado, let's start Unit 13. Unit 13 is basically the lab that you are doing right now, except we've already talked about how to do it, so this is going to be really easy. So let's go ahead and get started here. So, first thing we're going to define is an empirical formula. An empirical formula is the simplest ratio of elements in a chemical formula. And so what that means is that if we have a ratio like this, I can't divide anything out without making fractions. So this would be simplest, this would be simplest, but this would not be, because I could divide both by 2 and get a simpler ratio, right? So these are all the simplest possible ratios. 1 does not necessarily have to be in there. You just have to have divided out all the numbers that you can. Kind of like lowest common denominator, that sort of thing. When will the Unit 13 and 14 quizzes be posted? Not sure. They're not going to be due on Thanksgiving or on a day that there isn't class, though. So probably week 10? Sometime in there? Like, if we finish this on Tuesday or Wednesday, I'm not going to put the quiz up on Wednesday and have it due on Thursday. Like, that's silly. That's a holiday. So in that case, it would be due, like, Monday or Tuesday, week 10. Where you could work on it through Thanksgiving if, like, you hate your family and you just, like, I would rather do anything. Well, then I will give you the option to do your chemistry quiz, because I am there for you. But no, nothing will be due during the holiday. Or on the holiday, I should say. All right. So there's the simplest ratio. So we're going to be looking at formulas and saying, oh, okay, is there a number that we can divide out? So in NF2, there is no number we can divide out. There's a 1 and a 2. But in N2F4, I could divide each of these by 2. And then I would get NF2 as my empirical formula. Now, empirical formulas do not necessarily exist. So something like this. This is a molecule that exists. But if I turn it into its empirical formula, this is not a molecule that exists. So empirical formulas are just a sort of model, theoretical type thing. Okay, so don't be surprised if you get a formula that's like, wait, this doesn't make any sense. It doesn't exist. Because it might not. This is driving me crazy. Why isn't this clicking? I'm sitting here clicking on this for like, why isn't this working? Is my mouse just screwed up? There we go. Okay. I don't know what the deal was with that. That was weird. All right. So I'm going to put some on the screen here, and what I want you to do is tell me which ones are empirical formulas and which ones are not. And if it's not an empirical formula, reduce out the lowest common denominator and tell me what the empirical formula is. Okay? So go ahead and do that in the chat. I'll give you like a minute to do that because this shouldn't take very long. All right, so let's go over the answers here. So for CO2, there's no number I can divide out, yeah? Because if I divide by 2, then I would get a fraction for this first one. So this one's good. Oops, there we go. For the second one, for hydrogen peroxide here, I could divide each of them by 2. And I get this. Now, no, this is not hydroxide. Hydroxide is OH minus. OH with no charge on it isn't a thing that's common. I think you can make it in a high energy lab setting. But it's very uncommon. So be very careful because the charge is very different. This is very common. Hydroxide is very common. This one, however, is not. This is just an empirical formula. For number 3, I can't divide out a number. If I divide by 2, then 3 becomes fractional. And if I divide by 3, 2 becomes fractional. So this is fine as is. And then this bottom one here, I can divide by 2 again. And I get this. Which, again, is not necessarily a thing. It turns out this one actually is a thing. Wait, is this one a thing? No, it's not. This is not a thing either. I was thinking of something else. So again, empirical formulas are just models, and we get them by dividing out the common number that is present in all of the elements. Now, why do we care about this? You might be asking. And the answer to that is because if you're trying to figure out the formula of a compound, it's not very easy to do so. And I might have a picture of that in a second here. Actually, let me see here. So if I do this, I don't see the picture. So what I'm going to do is I'm going to draw the picture. So we'll go over here. And I don't care about that thing at the top. But let's suppose that you were trying to identify something that had carbons and oxygens in it. And so you knew you had carbon and also oxygen in it. And so what you do is you put it into a device or have it undergo a reaction that would split it into carbon and oxygen. Now, it's impossible to split one molecule because molecules are so small, right? So we can never really just grab one. We don't have molecular tweezers that allow us to do that. If we put stuff into this device, it's going to be billions and billions and billions of molecules, and we're just going to get a mess of carbon and oxygen. Yeah? So what we'd end up doing is we'd end up getting something like this, and I got to make the brush size bigger so I can just go like this. So doot 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 doot. So there's my carbon, and then for my oxygen I'd be like doot 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 doot. And because I have a stylus here, they're all coming out different sizes. There we go. Now, if you were looking at these bins, something that you could do is you could say that there is twice as much oxygen as there is carbon. And you can see that, right? Like I tried to draw 4 rows as opposed to 2. Although I don't know why they all kind of crowded at the bottom and then fanned out at the top. Whatever, right? And so what we would say is that the empirical formula would be this. Because in the empirical formula, there is twice as much oxygen as carbon. Now, is what we put in here CO2? Well, it could be. Because CO2 has twice as much oxygen as carbon, right? But so does this. If this exists, which it turns out it kind of does, it does as an ion, this could be what we put in the detector, because there's twice as much carbon as oxygen. So this is possible. As are any combination of things that have twice as much oxygen as carbon. But this cannot be what we put in the detector, nor could this or that. Because these do not have the same empirical formula as what we observed in the device. So empirical formulas are a tool that help us figure out what the formula of compounds is related to. And we know that in this example up here with my carbon and oxygen, everything points to it being twice as much oxygen as carbon. It would be one of these formulas right here. So it helps us narrow it down. Now, how do we get the rest of the way there? How do we figure out what exactly it is? And the answer is that we weigh it. And it turns out you can weigh individual molecules because we have a technique for that. And we're going to talk about it more in 161, but the gist is that to get the molecular formula of the compound, you weigh it. And the device that is used is called a mass spectrometer. And we're going to talk about that in 161. I have studied the mass spectrometer usage. I'm an expert in mass spec. This is literally all I did in grad school. Was I would make something and then I would go throw it in the mass spec. Did I make what I expected? Is there a peak at 78? And if there was, I was happy. And if there wasn't, I was sad. More often than not, there was no peak at 78. What does all that mean? We'll talk about it later. But the gist is that you accelerate molecules, not individually, but they all get bent through a magnetic field based on their weight. And the heavier they are, the less they bend. So you can calibrate it to say, oh, okay, if stuff hits the detector, it must weigh this much. And then you can figure out very accurately what things weigh. So that's how we get the molecular mass of something. And we do that in this process. So if I know what the factor is that converts one of these to the other, I can multiply the empirical formula by that factor to get the molecular formula, whether I'm looking at the formula or the molecular weight or mass. So this works for either of them, because if I'm multiplying the formula by a number, I could just multiply the molecular mass by a number. If CH2O weighs 30 grams per mole, then C6H12O6 must weigh 6 times as much, or 180. So if I know the mass of the molecular formula, and I know the mass of the empirical formula, which you can because you have it, you can get this multiplier. Now here you can easily see, oh, I'm just multiplying by 6. So the multiplier for this one would be 6 to get from the empirical formula to the molecular formula. There will always be a multiplier to get from an empirical formula to a molecular formula. It is possible that the multiplier is 1. So an empirical formula can be a molecular formula, but it is not always required to be. All right. Now, how do we do this in the laboratory? If I gave you a mass spectrometer and a sample of substance that could do elemental analysis, in other words, what it does is it breaks your elements into those piles that we saw over here and then weighs them for you, then you could solve for the formula of any substance quite easily. And so what we're going to do is this strategy here. So the first step is to take all the masses that you get from your elements and turn them into moles. I guess that was the first 2 steps. I was going to combine them into one. So you need to know how much of each element you have by weight, and you can do that very easily. You just use a balance, right? Will the multiplier ever be anything but a whole number? It has to be a whole number. Because if it's not a whole number, you will get fractions, and you can't have fractional atoms. So you can't have O3 halves as your number. Now, there are some possibilities where you can end up with fractions, and you have to work to get rid of them. And we'll see an example of that in a little bit here. But we're always going to be multiplying by whole numbers to either clear fractions or to prevent fractions. But yeah, you'll always have a whole number. And if it doesn't look like it's a whole number, round it until it is. All right, so I'm going to give you the mass of the sample in grams. Either you do that in the lab and you determine it yourself, or I just give it to you. So step one is pretty much free. Then you're going to turn all that into moles. And then from that, you just turn it as into a formula. Because moles represent a number, and you could write a formula out of that. So if I had 1 mole of carbon and 2 moles of oxygen in my sample, I could just say that's the formula. Likewise, I could have any ratio of this. So instead, if this was 0.5 and 1, I could write that as CO2, right? Because they're off by a factor of 2. But you might be tempted to say, well, I'll just write them as the formula. And that's not a formula, right? Because you can't have fractional atoms. So in this case, what we would do is divide by the smallest number to make it a formula. Because 0.5 divided by 0.5 makes 1. 1 divided by 0.5 would be 2. So when you're writing formulas, we're going to do that strategy to express a result. So let's do an example here. I'm going to give you Freon. Freon was a common substance used as a refrigerant. What that means is that in your refrigerator, there is a small little compressor that has a refrigerant in it. And the refrigerant absorbs heat to evaporate from the liquid phase to the gas phase, which makes the inside of your fridge cold, because heat is being sucked out of your fridge to make this stuff evaporate. Then the stuff is compressed and moved to out of the fridge, where it can then release that heat and turn back into a liquid, so that you can have a cold box. That's how a fridge works. And we used to use Freon to do this. The problem that arose was that Freon leaks from broken compressors in fridges. So when people were throwing these in dumps and stuff, the Freon would get out, and it turns out it's destructive to the ozone layer. So the Clean Air Act has banned the use of Freon, and the ozone crisis of like the late 70s, early 80s or so actually got fixed. It's like the one thing humanity has done correctly with regards to climate. So you can read about the ozone crisis and the growing ozone hole over Antarctica due to the use of refrigerants like that later. But Freon 12 is a gas that exists, and it has a formula, and it has C's and Cl's and F's. Note that this is a chlorine, this is not a carbon iodine. And I have this information handy, and I want to figure out the empirical formula. Now, if I give you a percent mass composition, I would know that 9.933% of that sample is carbon. So if I gave you 20 grams, it'd be 20 times 9.933% would be the mass of carbon in that sample. Well, if I give you a mass percentage, here's the easy way to do it. If you assume that I gave you 100 grams of it, then these numbers times 100 grams is just this number of grams. So in a 100 gram sample, there's how much carbon you have. There's how much chlorine you have. There's how much fluorine you have. So that's what we're going to do for mass percentage samples. If I give you the masses as a percent composition, assume you have 100 grams, and then just write out the masses without the percent sign. And now we can turn it into moles. So that's trivial to do. Let's do that on this over here. Okay, there go all my little dots. Ooh, no. I almost deleted OBS. That would have been bad. I didn't have PowerPoint selected. If the screen ever goes completely dark and then I start cursing and the stream goes offline, you'll know that I have accidentally deleted everything. Which is something that I'm terrified of. I'm glad that there's a warning window, because I really don't want to do that. I can't actually read all of this, so I need to get it all on the screen. All right, so we can very easily turn grams of carbon into moles of carbon, right? All we have to do is go to the periodic table and look up what the mass of carbon is. Well, in a mole of carbon, according to the periodic table, there are 12.011 grams of carbon. So in a 9.933 gram sample, how many moles would I have? I gotta get my phone, or not my phone, my calculator here. You could use your phone. I have a TI-83 that's ancient, and I'm just used to using that. So in our 100-gram sample, we have that many moles of carbon. Okay, cool. Let's do the same process for chlorine and fluorine. So for chlorine, according to the periodic table, this one I don't know if I have memorized. 35.45? 453, okay. All right, and then how many moles are in that sample? 1.654. Okay. Do you see a relationship between the number down below and the number up above? So this number and this number. Can you see the relationship there? There is a multiplier between those, and you probably already noticed it. But we're going to do the same thing for fluorine. We'll turn it into moles. And then fluorine's 19, right? 18.998. Okay. I should really just get the periodic table on the desk and not lean over and look at it on the floor where it's sitting for some reason. I hit enter too early. Hold on. There we go. And when you do this, you'll notice, oh, look at that. Actually, what you get is 1.655 if I round correctly. But that's close enough, right? Those are essentially the same, chlorine and fluorine. So the last thing that we're going to do is we're going to make a formula out of this. So I'm just going to write it like this. Now, this is not really a formula. I'm in fact going to call it the pseudo formula. Because it's sort of a formula, right? It expresses the relationships effectively, but no formula exists like this because you can't have fractional numbers of atoms, yeah? So to get out of the pseudo formula to get to the empirical formula, we're going to divide by the smallest number. And so in this case, that ends up being carbon. So we're going to divide everything by 0.8270. And if you're following along with your calculator, you'll notice that dividing these two numbers together, you just get 2's, right? So I get a 1 here, and I get a 2 and a 2. I actually get like 2.001 whatever. But because that's so close to a whole number, we're going to keep it as a whole number. And so that's the result that we get. So we just take these numbers and we stick them in the formula. Because remember, moles are just counts of atoms, right? We just change the unit by a factor of Avogadro's number. So if I make a molar ratio, I'm creating a formula. All formulas are molar ratios. So that's how we find the empirical formula of a substance using its mass. And it's not hard to do. You probably could have done this on your own with maybe a little difficulty, but that's kind of my job, is point you in the right direction and show you an example. And now you can totally do it for any empirical formula you want to. So this walks you through that. There's the formula that we got. That's not really a formula. And so we divide by the smallest number, and there's your answer. So what I want you to do now is I want you to try and do that with this. I believe this is Wellbutrin. I think. So you have this ridiculous formula with 5 things in it. You're just basically doing the same thing that we did, except you have 5 of them now. So go ahead and try and do that. Turn them into a mass, turn the mass into moles, and then write out the pseudo formula to get you to a formula. Okay? I'm going to leave you about 5 minutes to do this. And when you get your empirical formula, type it in the chat for me. Okay? See you in a bit. Let's do 2 more minutes, and we'll go over the answer together. All right, let's go over the answer here. So what we're going to do is we're going to turn everything into moles. So let me clear that out of the way. And we'll just put those over on the side, and we'll get to work. So we're going to assume 100 grams. Which means that all these percentages just become masses. So we'll turn this into moles. 1 mole of carbon is 12.011 grams, according to the periodic table. And how many moles is that? I have 5.423. All right. Then we'll do hydrogen. So we'll turn that from grams to moles. And I get 7.51. And then we'll do Cl. And how many moles is that? That's 0.4172. So I got that. And then we'll do nitrogen. And nitrogen is 1 mole is 14.007 grams. And I get 0.417. And then for my oxygen, one mole is 15.999. and I get 0.417. So you'll notice there are a bunch of repeating numbers in there because those are all our ones in the equation here. So I'm going to take all of these numbers and I'm going to make them into a pseudo formula. So that's going to look like this. So C 5.423, H 7 point something, 7.51, CL 0.4172, N 0.417, O 0.417. And so there's our pseudo formula. We're going to divide by the smallest number, which is 0.417. And so these are all going to become 1. We round 4.172 divided by 0.417 to 1. 5.423. I typed it in wrong. Hold on. 7. So this becomes 13. And 7.51 divided by 0.417 becomes 18. So there's our results, and so we can write that as our formula. C13H18 ClNO. And there you go. So that's how you do an empirical formula. And it looks like most people got that right. Everybody got that right. Everybody who participated. Excellent. All right. So I've got one more for you here. Oops. So go ahead and try this last one here. This one I gave you grams, so you don't even have to assume you have a 100-gram sample. You just use the masses that I gave you. What is the empirical formula of ibuprofen? When you're done and you've got your empirical formula, go to Wikipedia and look up the chemical formula of ibuprofen. In fact, I'll even give you the link for it. Ibuprofen, Wikipedia. So you use this to check your answer when you're finished. To see, hey, did I actually get an empirical formula? So there you go. There's the Wikipedia entry for ibuprofen. So do this problem first, get your empirical formula. You'll find the molecular formula on this page. I'll give you 5 minutes to do it. We'll see you in just a bit. 1 or 2 more minutes, and we'll go over the answer. All right, this exercise has a little bit of a snag in it that comes up because when you do the pseudo formula and then you divide out the smallest number, you still get a fraction. And the question becomes, well, what do I do with that? So we're going to show what you do with that right here. Oh, excuse me. All right, so let me scroll this back up to the top. So we're going to do what we did before. We're going to turn everything into moles, which I can't see, unfortunately, because there's a window in the way. There we go. So let's start with carbon. And we'll convert that to moles. We've done that plenty today, so that's fine. Ooh, I typed the wrong number in. That's no good. And I got this, 0.6300 moles of carbon. Oh, 6301, sorry. There you go. Now we do the same thing for hydrogen. So we'll just cancel those out. And then we'll convert that to moles. 0.881, 1.008. And I got 0.874 moles hydrogen. And then finally we have oxygen. In 1 mole oxygen there are, that many grams of oxygen. 0.90694. All right, so there's a lot less oxygen than there are the others. Just be mindful of the 0, don't lose it. So now we'll make a formula out of it. C 0.6301, H 0.874, O 0.09694. We're going to divide by the smallest number. And I get 1 for oxygen. When I do hydrogen, I get 9.015. That's close enough to 9, right? But when I do carbon, I get 6.4999, right? What the heck? And the reason that you get a fraction is because when you do this method, coefficient, I misspelled it here. When you do this method, the smallest coefficient will be 1 because you're dividing a number by itself, right? So it has to be 1. But not all empirical formulas have a 1 in them. Remember that this was an empirical formula, and there aren't any 1s in it. So what we have stumbled upon is a formula that doesn't have a 1 in it. So what we have to do now is we have to clear the fractions by multiplying. So we don't do any more division, because that would just make numbers smaller and more confusing. But what we're going to do is we're going to multiply by something that clears a fraction. Well, if 6.5 is the same as me writing this 13 halves, I could then times that by 2 to clear the fraction, right? And then I'd have to times everything else by 2 to clear the fractions. And the result that I would get would be this, which is an empirical formula. And it turns out is the actual formula. Now, that's the second example we've done where there was a C13H18. Is this common? More than you would expect, but not like super common. So that's just sort of a fluke. I didn't actually notice that until just now. So if you get a fraction when you're doing this step right here, don't round from 6.5 all the way up to 7, just because you're rounding by a significant amount. That's too much. If you end up like 0.001 away, yeah, you can round that. That's okay. But if you're like more than 0.1, then start looking for situations where you might have to multiply. Now, are there any situations where you might end up with like 0.3, would you have to round a second time? So you won't end up with 0.3 necessarily, but what you could end up with are things like this. So you might end up with like 1.25 or 1.33 or whatever. So we already looked at this example where you have a 0.5 and you just times it by 2 to fix it. If you end up with a 0.33, you could times it by 3 to fix it. If you get a 0.25, you can multiply by 4, and so on and so forth. I think the most common ones that you will see are 2, 3, 4, and 5. I guess 5 would be this. So if you have one of these decimals, and when I say decimals, we don't really care about the 1, we care about this part. So if you have one of these in your pseudo formula, then you have to do this extra step to clear it. And that can happen because the process by which you are working sets one of the coefficients to 1. Excuse me. All right, let's see here. When we come back, we're going to do some molecular formula work. And we'll talk about how you take the empirical formula to get to the molecular formula, which is just a slightly different process that you're going to tack on to the end of everything we've done here. But that's for after the break. And I do need the timer up here. There we go. All right, I'm going to go put some more Paradise Killer on there because we're getting to the end of the quarter, and this is where I break out the good music. All right, see you in a bit. Yay! Landed right on 10, finally. Alright, welcome back. Not every day that we land exactly on 10. Last quarter I did it like 8 times. This quarter I think I've only done it once, so... Alright, so we've talked about how to do empirical formulas. Now we need to take the next step, which is to turn an empirical formula into a molecular formula. Oh, have I got it twice already? I don't remember. It all sort of blends together, I guess. So, how do you find the molecular formula? Like we talked about earlier, you need the molecular mass of the compound, and you also need the empirical mass, but you can calculate that from any formula. Now, the relationship between the empirical formula and the molecular formula is this multiplier n. Well, if I want to solve for n, I could just rearrange the equation to look like this. Whatever the molecular mass is divided by the empirical mass must be the multiplier. So if I know those two masses, I'm all set. So let's do an example here. Let's suppose that I find the empirical formula of a compound. I do all of the stuff that we just did earlier today, and the result that I got was this, CH. And then I learned that if I put this substance into a mass spectrometer to weigh it, I learned that it weighs this, 78.11 AMU, or grams per mole. It's the same thing. So this is going to be the molecular mass. This is the empirical formula, which means that its empirical mass must be C plus H. Now you can go to Lentech and just type in CH and hit enter, and it will give that to you. I'm just going to do it on my calculator real quick here because I have it. And there you go. So what we're going to do is we're going to say molecular mass. Oh no. Sorry, hold on. I hit the button and I immediately knew what went wrong there. Do I have to just click now? What is the deal here? Maybe the nub on my pen is getting too low and I need to like... Yeah, weird that that's not working. Molecular mass divided by the empirical mass. And that's going to equal the multiplier. So, let's type that in. 78.11 AMU divided by 13.019 AMU. Those cancel out. And when I punch those in the calculator, I get 5.99969. Well, I can't multiply a formula by that. I'm going to round that to the nearest whole number, which is 6. So that means that my CH multiplies by times 6 to become this. This is benzene. Benzene is super common and pretty carcinogenic. There you go. I've given you a problem that has cancer in it, I guess. I don't know. All right. And there is our walkthrough right there. All right. I'm going to have you do the entire process, start to finish. So I'm going to give you butane-dione, which is these element masses after it's been decomposed. First, I want you to tell me the empirical formula. And then once you have the empirical formula, knowing that it has a molecular mass of 86.09, tell me what the molecular formula is. So do it in this order. Do the empirical formula first, then the molecular formula. There are other ways to do it in a roundabout fashion using like percent by mass and whatever. I'm not going to talk about how to do those. I could work them out and follow your work, maybe, but obviously I can't see your work in this circumstance. So do it the way that I've shown you. Turn those grams into moles, turn the moles into an empirical formula, use the empirical weight and the molecular weight to get the molecular formula. Okay? I'll give you 5 or 6 minutes. Type in your empirical formula and your molecular formula when you have got them. See you in a bit. One or two more minutes, and we'll go over the answer. All right, let's go over the answer. We'll click over there. And over here this time, so I can erase everything without it yelling at me. Stylus, there it is. All right, so, I mean, we've been doing this all day by now, so. And the reason that I like this lesson is because it really just drives home the point of how to convert stuff from grams into moles. Like, we've done it so many times that by the end of this, you probably do it in your sleep. You'll go to bed and be like, grams to moles divide by the periodic table number. And then they'll think you're insane. That's what happened to me. So we'll do that with hydrogen as well. Grams to moles. This is how you also start memorizing these numbers from the periodic table. Is years of this. So there's my hydrogen, and then what else do I have? I have oxygen. All right, so there's that 18.59 over 15.999, 1.162. We're going to make a formula out of it. You might wonder why I do these curly brackets, because normally I'd write it over here, but there's not really enough space. If I had a whiteboard, that's what I'd be doing. So we got C, and I still have the number on my calculator, so I'll just copy it down here. H O, and we'll divide by the smallest number. And so I get 1.162 over 1.162 is 1. I'm assuming that this is going to be a 2. Yep, so that's a 2. And this is a 3. All right, so there's our empirical formula. Let's figure out its empirical mass, because we're going to need that for the next step. And this one's big enough that I will go to Lentech. So if I type in C2H3O, and I get 43.04, so we'll write that down. All right. Then the next part of the problem says, well, the actual stuff weighs 86.09, so the molecular mass is 86.09 AMU. Well, if I just divide that by the empirical mass, I'll get the multiplier, which is 2. So I'm going to take my formula, I'm going to multiply by 2, and I get C4H6O2. And that's the molecular formula. All right, that's how you calculate empirical and molecular formulas. There's one extra thing that we're going to be doing to finish off the lecture today, and that is to talk about combustion analysis, which is just an extended version of this. I'm going to talk through an example and show you how it's done, but you're not going to be required to do the next part. Everything up what we've done till this point in the lecture, you will be responsible for. So this will be on quiz number 8. But the next slide, what we're going to do, this is just sort of a preview. You're going to do this in 161. And I want to show it to you, but I'm not going to test you on it in this class. This is how do we do this in the real world? Like, what I'm giving you on paper is kind of a model. I'm giving you elements that we have neatly weighed out. But it turns out it's a lot harder to do that because oxygen is so abundant. And we use oxygen to burn things to break them apart. So this is called combustion analysis. You basically set all of your substance on fire and then weigh the products. But the products are not straight up carbon or just regular elemental carbon and regular elemental hydrogen and so on and so forth. You end up getting other things, namely oxides. For instance, if I burn anything containing carbon, hydrogen, and also oxygen, you get hydrogen oxide, or water, and carbon oxide, or CO2, as the products. And so this is always true. So if you have a hydrocarbon, which is just C's and H's, and you burn it with oxygen, you always get this. Likewise, if you have a carbohydrate, you get the same result. Now, if you are following the atoms show up in very specific places. For example, all the carbon that was in the hydrocarbon has to be present as CO2. So if you know the mass of CO2, then you know the moles of CO2, and from that you know the number of moles of carbon that are in there. Likewise with the hydrogen, same thing. All the hydrogen ends up in water, right? So if you know, we'll write this down here. So if you know the mass of CO2 or H2O, then you know the moles of CO2 or H2O, and then you know the moles of C or H. Because in 1 mole of CO2, there's 1 mole of carbon, right? In one of the big thing, there's 1 of the carbons. And in one of the waters, there's 2 hydrogen. It's all the stuff that we did in Unit 12. It's like it's designed this way. It totally is. Okay. So if we do combustion analysis with carbon and hydrogen, oxygen is optional. If there is oxygen in the formula or not, we still get the same thing. We just can't do the same thing with oxygen because oxygen from our substances gets mixed in with what we have added during the oxidation process. And we don't know what oxygen in that mass is from that without doing some roundabout math. So there's a more complex oxygen example. We're not going to do it today. But we are going to do the simple carbon and hydrogen one. All right, so here is our combustion analysis process. It is the same as the empirical formula process, except for we have to do the initial step of figuring out the number of moles of hydrogen and carbon from a mass of water and CO2. So we have an extra step snuck in, and here's what that looks like. So here's our sample problem on the board here. I'm going to burn a hydrocarbon with C's and H's. If I could find the cursor. Oh, it's because the pen is right there. Oh, there we go. We're going to burn a compound with C's and H's in it. And when I'm done, I get this many grams of CO2 and this many grams of H2O. So we're going to write this out. And so what we'll do is we'll turn grams of CO2 into moles of CO2. And we'll turn moles of CO2 into moles of C, because once I get to this point, I can then make a pseudo formula, right? So we'll do that. How many grams of CO2 are in a mole? Well, you can go look that up on Lentech. And then in one of the big thing, there is one carbon, because that's where the one is. I mean, you can't really see it, it's invisible. But there is one carbon in CO2. And so what mass do I get? Or not what mass, how many moles do I get? 0.0415. We'll do the same thing with water. And oops, hold on. We'll do the dimensional analysis first. And then in 1 mole of water, there's 18.0. Is it 18.16.2? We'll just do that. Nobody cares, right? And then in 1 mole of water, there are 2 moles of hydrogen. This is the important one. Make sure that you don't accidentally forget that this 2 is here, because remember, there are 2 hydrogens per water. Again, I'm not testing you on this, but that's okay. And then I can take these and make a pseudo formula. This might actually be a... Was there a... Did I miss a number? No, I didn't. Okay. So this becomes 1. You're going to notice that I'm going to get a fraction here. And that's okay. I times those by 5 to get rid of this 0.4. And there you go. That's how you do combustion analysis. So again, you're not going to have to do that. Just in case you are curious, though, and you want to do some of the exercises in the text, prepare for 161, where you may have to do that. Or you just want some extra practice, you could do these exercises. So there's our answer. I'm not going to do the example with oxygen here, because it's a lot longer, and again, I'm not testing you on it. You'll see that in 161, so you could try it on your own. The slides do walk you through it if you'd like. And then here's another one with CHs and Os in it. But that's it for Unit 13. That's all we're going to do today. We've got, what, 15 minutes left? I mean, I guess we can do this, so we could just go to the hooray orc. Hooray. And then, let me look at how many slides are in Unit 14 real quick. $20. Is there anything I can do in here in 15 minutes? This looks like it's a little, just barely too long, so guess that does it. All right. That's where we'll stop. We'll stop 20 minutes early. It's nice to have a break. You guys are working hard. I'm not working hard, but whatever. I'm in charge, and I'm an adult, and I get to do adult things. Adult things such as, like, make adult decisions about my life, not inappropriate stuff. I was like, oh, that could be construed weirdly. I should end the stream before I say anything else that will be misinterpreted. I do want to thank everyone for coming out to the lecture. Let me know if you have any questions on any of the material from Unit 13. There will be a quiz going up for Unit 12 I'm going to do that right now as soon as the stream goes down and I finish typing in all the parameters and stuff to get YouTube to start rendering it. That will be due next week. The next quiz is Units 13 and 14, and that'll be due after Thanksgiving at this point, because we're going to finish Unit 14 on Tuesday, and then Wednesday is just going to be a random Q&A for whatever. We're not going to need to do extra lecture, so... Oh, there's that music. I guess that means it's time to go. Have a wonderful evening, and I'll see you tomorrow. Take care.